I think I'll just start again. Right, we started to look last time at the gross structure of the Earth as a planet, and we'd looked a little bit at the hydrosphere and the atmosphere. I'm going to mention very briefly the energetic balance of the Earth's surface, because that drives a lot of the processes that we're really interested in, though we won't really look at them at a planetary scale again during the course. So there are two pictures here. So that is the Earth seen from space, and that is the Sun seen from space. And you probably feel that that looks a bit hotter than that. You'd be right. And that temperature difference has quite a profound influence on the way that the Earth actually works. Black body spectra, yeah, remember those? Yeah, little bit of nodding. Okay. There's quite a lot of information in this diagram, so I'll take a minute or two to walk through it. If you sat out in space and looked at the Sun, then what you would see would be a body that apparently was at about 6,000 Kelvin, because that's the temperature of the Sun's surface layers. And similarly, if you sit out in space and look at the Earth, then what you see is a body that is at about the temperature of the top of the Earth's atmosphere, which is round about 288 Kelvin. So the Sun is a black body emitter at about 6,000 Kelvin, and because the wavelength of the radiation emitted depends on temperature, the Sun's emission temperature is in this region of the spectrum, so from sort of 0.1, 0.2 of a micron up to a few microns in wavelength. The spectrum here is the absorption or transmission, whichever way around you want, spectrum of the Earth's atmosphere. So we've got 0% transmission, 100% transmission, and helpfully this has been divided up into more familiar regions of the spectrum like UV visible, infrared, and long wave infrared. So you can get a feel for where you are in the spectrum. So down here in the UV, you can see that the atmosphere is essentially opaque. There is 0% transmission. And that's a good thing because, that opacity arises from absorption by ozone and at lower wavelengths again, oxygen. But it's the ozone that's important because the ozone just nips off this UV tail in the solar radiation. So you get very little solar UV coming down to the Earth's surface because the atmosphere is essentially opaque. Across much of the visible region of the spectrum, you can see that the atmosphere is pretty much completely transparent. And then out into the near infrared, again, the atmosphere is pretty transparent. And this region, where the atmosphere doesn't absorb very much at all, corresponds to pretty much the maximum intensity of the incoming solar radiation. So a lot of the solar radiation will make it down through the atmosphere to the Earth's surface. And I mean it's about 340 watts per square metre hits the top of the atmosphere, and about 100 watts per square metre gets bounced off or reflected. So about 240 watts per square metre of solar radiation actually hits the surface of the Earth. Now, in terms of the energetic balance of the Earth, you've got the Sun putting radiation energy in the form of radiation, and quite a lot of that makes it down to the surface of the Earth and is absorbed. Now, if the Earth isn't going to heat up and heat up and heat up, then there must be an energetic balance. and the amount of solar radiation that comes in must be pretty much balanced by the amount of radiation that the Earth puts back out into space. But because the Earth is a cooler body, its emissions are out here in the longer wavelength, so very much in the infrared region. And if you look at the infrared, you can see that the atmosphere is largely opaque across big chunks of the emission spectrum. We've got a few areas here, and to a lesser extent here, where we've got some degree of transmission. But this lot really is important because this is, if you like, this is the window that lets outgoing infrared get back out into space. And you'll see that there's a bit of a bite out of it here, which arises from the absorption of CO2. And that diagram summarises all the concern there currently is about energetic balance and global climate change, because if you put more CO2 into the atmosphere, you're going to decrease the extent to which infrared can come out through that fairly narrow window, and you're going to trap more energy in the Earth's atmosphere, with all the consequences people then start to pontificate about. So I include that really just to give you a feel for how the energetics of the Earth's surface are driven. Okay, so a little bit more detail. You've got 100% of the inventory comes in, about 35% reflected, 65% comes down and goes back, and there are various pathways like reflection from clouds, absorptions at the surface, re-radiation from the atmosphere, re-radiation from the clouds, and so on. And you can find out about what's gone on historically in the Earth's atmosphere by looking at ice cores. So these are from polar ice caps, particularly from Antarctica, though Greenland is also useful. And excuse me. And then what they do is they simply give you a preserved historical record of what's gone on in the atmosphere. Because snow falls, it doesn't melt, it gets buried by more snow, it gets compacted, and it turns from snow into ice over a period of time. And the gas that was trapped in that snow when it fell remains trapped, becomes little bubbles within the ice core. And if you take a piece of glacier ice and put it in your Bob tonic, it actually fizzes quite violently because of all these little trapped bubbles being released from the ice. So, but if you do something a bit more scientific with those bubbles, other than look at it in your Bob tonic, then you can take the contents of those bubbles, and that's a trapped relic of the atmosphere at the point that that snow fell and was converted into ice. And you can start to play games with it. So here, looking at CO2 concentrations, this is an ice core from Vostok in Antarctica, so that goes back several 100,000 years, and you can make direct measurements of the CO2 concentration in those trapped bubbles, all the way from present back to several 100,000 years. And you can see how much the CO2 concentration has varied over time, from less than 200 ppm at the minima up to close to 300 at the maximum. You can also, by doing clever things with oxygen isotopes, you can also make an estimate of what they call the paleotemperature. So what was the temperature at the point where you had any particular CO2 concentration? And these are the paleotemperatures relative to the present. And I think you would agree there is a reasonable correlation between the two data sets. In other words, high CO2 seems to follow high temperature, and low CO2 follows low temperature. which is not the same thing as saying high CO2 causes high temperature. Correlation is not causation, to borrow a quote from somebody. All it says is that the two things seem to follow one another. It might actually be that if something else causes the temperature to warm, then you get more CO2 in the atmosphere. So it might actually be that it's cause and effect. Or it may be that both are actually driven by something else. But nonetheless, there is this relationship between high CO2 and temperature. And given what we've done recently, I can't remember if I stuck that in the slides. No, I didn't. We've pushed a lot of CO2 into the atmosphere, and we're way up here now, well over 300 ppm CO2. And the question is whether that genuinely will be reflected in a spike in temperature at some point, because of course the system takes a long time to respond. And that's what all the drama queening is about climate science. It's whether 360 ppm CO2 really matters or not. So that's almost a little aside. I'll come back to the main body of what I want to talk about the building blocks of the solid Earth. And we're going to do some very straightforward stuff. It's explaining a bit of terminology and a little bit about how some of the most common building blocks of the solid Earth actually work. So I'm going to do a couple of definitions. I'll expand a bit on them, explain why they are as they are. We'll look at the compositions of some typical minerals. We'll look at the origins of rocks, how they form. We'll look at particularly silicate minerals, which are some of the most important groups that we find. Look at their structures and their chemistry. So what are minerals? Minerals are the building blocks of the solid Earth. You put minerals together in an assemblage, to use the term, and they are and they then become a rock. Now, some rocks are comprised of one single mineral. Some rocks are very complex mixtures of many different minerals. And we'll look at examples of both types as we go along. This next bit here, this is a formal definition of a mineral. So there are certain criteria a material has to satisfy if you're allowed to call it a mineral. It's a solid chemical compound. Okay, that's fine. With a definite composition. Okay, well, we're used to that because you get jars of compounds in the teaching lab the whole time. This is a slightly odd bit. Or by a composition lying between definite limits. So, compositionally, something can be a mineral, whereas you would not, with an inorganic chemist's hat on, consider it to be a compound. We'll look at examples in a minute. And with a characteristic ordered structure. So the world is full of amorphous crap, and I've spent my life doing research on the chemistry of amorphous crap, it sometimes seems. Amorphous crap is not a mineral, because it doesn't have a characteristic ordered structure. And here are some examples of what are minerals, but which you might not necessarily think of as being sort of compounds necessarily. So the first example are two of the polymorphs of calcium carbonate. There's a third one, a thing called vaterite, but that's rare. If you analyse the mineral calcite and you analyse the mineral aragonite, in both cases you will get the answer calcium carbonate. The reason they're not treated the same by mineralogists is that structurally they are different. And that means that their morphologies are different and their properties are different. So that's a picture of calcite, which has the odd property of what they call double refraction. So if you get a nice transparent piece of calcite and look through it at a single image, you see two images, because the refractive indices differ so much along the different crystallographic axes. That's aragonite, structurally different in the way the calcium and carbonate ions are arranged within the solid. So calcite and aragonite, they're both solid chemical compounds with a definite chemical composition, but they have different characteristic ordered structures. Therefore calcite and aragonite are different minerals. The point about composition within definite limits is illustrated here by the mineral olivine. So that's a picture of olivine. That's its structure. Well, so you've got it done that way, and you've got a space filling version there. Now, olivine is a silicate mineral, so the lattice is really constructed of isolated SiO4 4- tetrahedra, and the charge balancing can be provided by either divalent iron or divalent magnesium, or any mixture of both. So you can get a whole bunch of samples of olivine, and some of them might be pure Fe2SiO4, in which case it gets the name phthalate, or it might be pure Mg2SiO4, in which case it gets the name forsterite, or it can be anywhere in between. So you could have 9/10 of the metal ions being iron and 1/10 magnesium, or you can have a 50-50 mix. But regardless of the cation composition of an olivine, the structure is always the same. So olivine qualifies as being a mineral because it's a solid chemical compound with a composition lying between definite limits. The limits in this case are pure Fe2 and pure Mg2. And it has a characteristic ordered structure, so it ticks all of the boxes in that definition, and olivine is a mineral. Didn't realise they went round. Okay, so hopefully they'll stop, because I'm feeling slightly queasy looking at them. The point about this is just an illustration of how different the structures of calcite and aragonite are, the two calcium carbonate polymorphs. In calcite, the calcium ions are 6-coordinate bicarbonates. In aragonite, which is is a very different structure, you actually have 9-coordinate calcium ions. So the ions within the structures are totally different in the way they're arranged. Now, sometimes you find minerals where you don't have complete flexibility of composition, as you do with the olivines. And again, I'll pick another example here, the so-called alkali feldspars. Mineralogists really like their sort of 19th century nomenclature. So the alkali feldspars are so-called because you had alkali metals, group 1 cations in there, balancing the charges. Almost always sodium or potassium. We'll look at the feldspar structure later, but compositionally, these are all M, where M is either sodium or potassium, AlSi3OA. And in the low temperature version of the alkali feldspars, you can't just swap sodium and potassium willy-nilly. There are certain limits within which you can swap them, but then once you go outside those limits, you actually find that the structure becomes unstable, and you get structural rearrangement and separation of phases and phenomena like that. And that makes sense, because looking here, sodium is much smaller than potassium, so there is a point at which the lattice can't cope with swapping smallish cations for biggish cations. And there's a bit of terminology here. This phenomenon is known as isomorphous substitution. For those who know any Greek, iso meaning the same, morphous relating to shape. So this is substitution of one cation for another without affecting the shape or the structure. It's also sometimes referred to as solid solution. And where you get minerals of this type, where you've got compositional variations without structural change, they're sometimes referred to as solid solution series. I said we'd get on to the silicates, so here we are. This takes a little bit of digesting. The place to start is with the simplest silicate. So the simplest thing to do with silicon in a mineral is to put 4 oxygens around it to give you a tetrahedral SiO4 4- unit. And that's what we saw in olivine. The structural unit of olivine is SiO4 4-. So these little tetrahedra are represented in these diagrams like this. So you've got the silicon sitting in the middle, and you can identify the 4 corners of the tetrahedron, and at each corner you have an oxygen atom. So that's the simplest thing we can do. We have the formula SiO4 4-. We have 1 silicon to 4 oxygens. The example I've given you is olivine. And that, being an isolated tetrahedron, obviously shares no corners. If you're a bit short of oxygen, then maybe what you will do is you'll start to share corners. And rather than 1 isolated tetrahedron, you'll join 2 tetrahedra together through 1 shared apex, like so. So that is now Si2 for the 2 tetrahedra, O1, 2, 3, 4, 5, 6, 7. And overall the charge on that is 6-. So that's the simplest way to economise on oxygen, is to share 1 corner, to have those as your anions. Your silicon oxygen ratio is now 1 to 3.5. And the rather weird mineral hemimorphite that we won't mention again is an example. And you can carry on joining corners together. So we can take 3 tetrahedra sharing 2 corners each, which gives us then well, it's an Si309 6- or SiO3 2- if you were to boil it down. Silicon oxygen ratio now 1 to 3, and you've got the mineral tourmaline, which is a semi-precious stone, because I know this because I had to buy one for my wife recently, because she likes shiny things. Or the alternative way of carrying on sharing corners is to assemble chains like this. So here we've got a chain of silicate tetrahedra, each sharing 2 corners, and the chain just running on indefinitely. And that's another way then of giving us SiO3 2-. And these are more common minerals, pyroxenes these are. So they're quite a common class of rock-forming minerals. You could take 2 of these chains and you could stick them together. So now, as well as sharing along the chain, we're sharing across, like so, to another chain, giving us this structure, this double chain. So now we're down to Si4O11 6-, and we're 1 to 2 3/4 in the double chain minerals. Big smart, you've worked out what you can do next. You can keep going. You don't have to just stop with a double chain. You can add more onto these oxygens and these oxygens. And then you've gone from a double chain to a sheet. So you've got a 2-dimensional array of silicate tetrahedra, now sharing all 3 corners. And the sheet silicates are Si2O5, 2 minuses as the building block, 1 to 2.5 silicon oxygen ratio. Characteristically, these are the minerals we call micas. And finally, you can share all the corners of all your tetrahedra. The thing to notice here is that to do this, here in this sheet, all the tetrahedra are pointing in the same direction. So if you want to think of all of these unshared oxygens pointing upwards out of the screen, to make it work in 3 dimensions, you've got to join upwards and downwards. So you need to have half your tetrahedra pointing upwards and half pointing downwards. And that's what this illustrates. So if you like, the empty triangles represent tetrahedra where the oxygen is pointing down into the screen and can join up with an oxygen underneath. And these filled triangles represent tetrahedra where the apical oxygen is pointing out of the screen and can join with another layer which is out here somewhere. So by making that structural change, you make it possible then to stack in a 3rd dimension, and this gives you your framework silicates. You no longer have any oxygens unshared, so all 4 corners of all the tetrahedra are shared. Your formula comes down to SiO2, electrically neutral. Your silicon oxygen ratio is 1 to 2. The mineral quartz is a classic example. And feldspar minerals, which we met a minute or 2 ago, are framework silicates whose structures are derived from the idealized quartz structure. So that's a walk through the principal structural types that you find in silicate minerals. And we'll look just at a couple of examples here. So we have the feldspars, we've talked about them. What you do with the feldspar is you take that 3-dimensional SiO2 structure and you replace a proportion of the silicons in the centres of the tetrahedra with aluminiums. So your structural unit becomes AlSi3O8 or Al2Si2O8. And obviously, because aluminium is trivalent and silicon is tetravalent, you have a charge imbalance. You're short of one positive charge, and you compensate that positive charge by putting in potassiums or sodiums or calciums. And these give rise to 2 distinct series of minerals. We've met the alkali feldspars already, and there are a whole bunch of different names depending on their composition. So albite is the pure sodium alkali feldspar, and orthoclase or microcline, depending on the structure, is the pure potassium alkali feldspar, and you have a range of different ones in between, which I won't bore you with the names of. The other thing you have is you can have substitution of sodium for calcium, but because calcium is divalent, that is coupled with changes in the aluminium-silicon ratio. So you can have a range of different intermediates along here with varying sodium, calcium, aluminium silicon compositions, but all structurally basically the same, and all therefore members of this family. You often find, if you read around, that FSP is used as an abbreviation for feldspar. So KFSP tells you it's a potassium feldspar, or calcium FSP, calcium feldspar. What else have we got? We've met quartz. That's the 3-dimensional lattice of all the silica tetrahedra stuck together. composition SiO2. We've met olivine with its compositional variations between forsterite and fayalite. Amphiboles are the double chain minerals. So you've two silicate chains stuck together. They're quite variable. Well, they've got structures which can accommodate a wide range of different cations, so you get these very variable compositions. You also find that you can get a bit of hydration, so you get a few hydroxides hanging around. And they're just a couple of examples of amphiboles. Pyroxenes are the single chain, again, so that's quite a nice simple one, dioxide. Augites, rather more variable. And you can see in some of these you get variability in the aluminium silicon ratio as well, so you can start to put aluminium into those tetrahedra again, which then increases the diversity of the charge balancing cations. Micas are the sheet silicates, muscovite, white mica. That's a fairly idealised formula. Biotite is dark mica. Note that in both cases you get aluminium silicon swapping as well, and you can get a bit of hydroxide of fluoride. I'm not wanting you to learn mineral formulae and the like. I'm just trying to give you a very brief flavour of the types of minerals that are around, and in spite of their immense variability, the way it is possible to rationalise their structures. Okay, so how do you go from a mineral to a rock? Rocks are an assemblage of minerals. So you can take a whole bunch of minerals, stick them together, and it's called a rock. The minimum number of minerals to make up a rock is 1. So something like limestone, it can be essentially pure calcium carbonate, pure calcite, or occasionally pure aragonite. So limestone is a rock, it just happens to be all made up of one mineral, calcite. Other rocks are much more complex, and you have many different minerals that make them up. And we're not going to go into the pain of igneous and metamorphic petrology. We're just going to have a little dip into it, well, probably in the next lecture now. But what we can do is we can start to classify the immense variations we find as we go around the surface of the Earth in different rocks. There are huge variations in texture, in composition, in mineralogy. And to try and make some sense of it, the first thing to think about is actually where that rock originated. So the first split in the whole family of all known rocks is origin, and that's either an igneous rock, where you take a hot molten material, which is usually a silicate, not always, but almost always, and you allow it to crystallise, and as it crystallises it grows different minerals, and the resulting assemblage of minerals is a so-called igneous rock. Or you can have sedimentary rocks, and they form really through physical transport and deposition processes. So, for example, you can simply erode away quartz, silica, out of an existing rock, transport it around, dump it somewhere, squeeze it, cement it, and you end up with a rock that you would call a sandstone. Or you can generate a sedimentary rock through chemical precipitation. You tweak the chemistry and you get supersaturation and you get precipitation of something like calcium carbonate, which makes up a limestone. And the third group of rocks are when you take an existing rock and you do something bad to it. You squeeze it, or you heat it, or you do both to it. And that can lead to, if you remember last week we talked about subduction, partial melting, generating magmas that rise up in beneath, around subduction zones. those sorts of processes are obviously going to lead to structural and chemical change. The rocks that go down there will be different after that, those sorts of treatments. And therefore what we find is that the rock itself is altered, the minerals are different compositionally, texturally and so on. Metamorphic rocks are truly, truly a nightmare to understand. They're very complex. We might just look at one or two examples. I'm going to stop because we'll just get started on this and then we'll have to stop again. So I shall see you next week. Thank you very much.